In this video here, we're going to look at a variety of ways we can try to understand the surface, try to analyze it, and try to examine and extract a variety of topographic characteristics and properties of a surface. And this is also known as terrain analysis. A lot of these techniques and methods we've already discussed, and so it's essentially going to build upon previous discussed information on the raster data model and also those neighborhood operators, the whole local, focal, zonal, and global, but also the good friend of ours, the raster calculator, will also be used. What we're going to be doing is we're going to look at slope, curvature, hillshade, aspect, and cut and fill. Those are the types of techniques that we'll be focusing in on this particular module and the accompanying exercise. Generally speaking, digital elevation models, what we see here, DEMs, and triangulated irregular networks, or TINs, are the types of input data that are used to then create a variety of output grids that we'll look at. There are more options in these, but these are typically the ones most likely to be used in these types of analyses. In my example video here, I'm using a 10-meter digital elevation model. This is from Story, Indiana. This is in south central Indiana, an area of Brown County that kind of overlaps into Jackson County. Why do we choose this particular DEM, this location? Well, first off, it's ruggedness. It's one area of Indiana where you're going to see enough ruggedness that gives us stuff that we can look at and analyze and talk about. Also, it's an area in which I live close to it, nearby, and so it's an area in which I kind of have an understanding of the local topography myself. Further, we'll be working with this data set in the next module. So Story, Indiana, you're going to become quite familiar with it. A very important warning is all the elevation-based calculations assume X, Y, and Z coordinates are in the same units. What I mean by that, X, Y, and Z are in feet or meters, what have you, but they're all the same. The first technique that we're going to use to analyze the surface is slope. This is one that most of us are already familiar with, but this is calculated as the vertical difference between 2 points divided by the horizontal distance between those 2 points. And so essentially here is I have an example of a point that's located at 2, 4. Those are the X and Y coordinates, whereas point 2 is located at 5, 2. And so we're going from point 1 to point 2. So we're going to go down in this case. And so we do the old rise over run. Many of you are already familiar with that. So what we have here is 2 divided by -3 equals -0.66. And that makes sense. A negative result makes sense because we're going down the slope. If we're going up slope, it would be a positive number in this case. So this is also representing 0.66. So this is a 66% descent, in this case expressed as a percentage. So as far as a more formal definition of slope, it's the rate of change on a topographic surface. And so in the case of GIS, when we think about a raster, we have the kind of visualized as a grid here on the left. And think of that as it's the maximum rate of elevation change from each cell relative to its neighbors. Now was that local, focal, or global? Ding, ding, ding if you said focal, because it looks at each cell in relationship to its neighbor. So once again, it identifies the maximum rate of change in value from each cell to its neighbor. In the case of slope, 2 main ways in which it's defined or described: percent slope and slope degree. So essentially, there are 2 different ways to describe the same thing. Geographers, we tend to use degrees more, but percentage is often used for the general public to explain to the lay public. But in geography and in GIS, oftentimes we use degrees. Also keep in mind, this is only using the X and the Y coordinates here. So this is an illustration that does not include the Z coordinate as well, which is also used to calculate slope, like you've already done beforehand with those triangulated irregular networks from a previous exercise. Here's how we would calculate slope in ArcGIS Pro. We put in our input raster, so the input is our DEM, and the output, in this case, the grid that designates or shows slope. In case here, we have 2 different ways in which we can have the output measurement. We could do it in degree or percent rise, and the default, as it's shown here in ArcGIS, is degree. If for whatever reason we had a DEM where the X and the Y units were different from the elevation or the z-coordinate, then we can use a z-factor conversion here. So in other words, if your DEM uses meters for the x and y, but for the z-coordinate it uses feet, you'd punch in a conversion rate or a z-factor of 0.3048 because 1 foot equals 0.3048 meters, as the ArcGIS explains here in the info pane. So basically what this shows here, this particular output grid, is the relationship of each cell to its surrounding neighbors in terms of the maximum change in topographic variation. Essentially what that means is areas with minimal slope or no slope are shown in green, as we can see here in this particular river valley and subsequent floodplain. And those are places that have zero to hardly any slope, shown by closest to zero in terms of our values. Areas with the steepest terrain are shown in red with up to over 40 degrees. And what we can see is the ridges are actually these green areas. They're kind of hard to see, but the ridge tops are actually kind of flat. The tops of a ridge is rather flat. Where the steep part is going from the ridge down to the flat valley floor. And so where we see these red parts is really where you see a increasing descent from ridgeline or the top of a hill down to the bottom, and those typically are going to be where we find ravines, creeks becoming streams, becoming rivers, in this very dendritic pattern, very much like trees and branches working their way to a bigger trunk. So that what I can do is I can put this in 3D, we could really start to see this. We can see the green, the flat areas here, the valley floor, but also the ridge tops. See how these ridge tops are kind of flat. I mean, the tops of these are scenic areas in Brown County often, are these ridge tops. Meanwhile, when we go from the descent, and this very steep face here, another steep face over there, and so these slopes are quite severe here, where they're shown in red and dark red in particular.